Okay. Good afternoon, everyone. My name is Linh, and today I'm going to present my joint work with Ackermann and Aquinas. We will provide an efficient solution to inverting the Ackermann function. Emphasize on the word efficient, among other things. And so, this is the Ackermann function. It's a recursive function, and it grows faster than any primitive recursive function you can think of. We are interested in a diagonal Ackermann function, which is a of n, defined as the Ackermann of n and n. So, as you can see, this function grows extremely fast. A of 4 is huge, and A of 5 is so big, we can't write it here. So, the inverse Ackermann function, alpha of n, is defined to be the minimal k for which A of k is larger than or equal to n. This function grows extremely slowly, but it's still hard to compute. For example, if you want to compute alpha of 100, which is 4, naturally we want to compute alpha of 0, A of 0 until A of 4. But A of 4 is a huge number that we have seen just now, and it's very inefficient to compute this number just to return 4. And so in practice, people use a lookup table where you get 4 every time the input is larger than 61, where 61 is A3. And so, but today we aim a little bit higher, which is to correctly compute the inverse Ackermann function for all inputs, no matter how large they are. And to achieve this, the key is to compute alpha without using A at all. This is our solution, formalized in Coq, and it fits into one page. And as you can see, there are 3 functions that build up to the last function. And by the name suggests, this function runs in linear time, which we'll get to later on. Okay. To offer a little bit of intuition before we start, we are inspired by the similarity between the Ackermann function and the hyperoperations. And if you look at n as an index and b as the main argument, you can organize the Ackermann function into a tower, much like the hyperoperation. In fact, if you add 3 to b and minus 3 to the result, it has been proven that you get the hyperoperation of the same level. And so, but more importantly, you can build the inverse towers by providing the inverse function to each of the individual levels in each of these 2 towers. And so, we are able to redefine alpha in terms of alpha k, which is the inverse Ackermann tower that we have seen just now. And if we are able to build the inverse Ackermann tower independently from the original tower, we can compute the inverse Ackermann function more efficiently, because we don't have to compute all the big numbers in the original tower anymore. So this is the plan. The first step, we want to compute the hyperoperation and the Ackermann hierarchies in a more functional, more elegant way with something we call repeater. And then by inverting repeater, we can build the inverse towers independently from the original towers, and we call it countdown. And next, we go to the main business, which is to compute the inverse Ackermann function and prove that it runs in linear time. So let's get to step 1. If you look at the recursive rules for the hyperoperation and the Ackermann function, at first they don't seem very similar. But by indexing and using b as the main argument, actually these 2 rules are the same. Moreover, we can build the next level with the previous level. So let's try to do this. Let's start with the n plus 1 level. If you apply the recursive rule once, you get 1 instance of the nth level outside. If you apply it twice, you get 2 instances of the nth level outside. And you can go on until you exhaust the main argument, at which point you get b instances of the nth level outside. This is what we call repeated application of a function to an initial value. And those of you who are familiar with iter in many languages, Coq included, have already realized what's going on here. So we call this repeater, but they are the same thing as iter. But by calling this repeater and using this notation, we kind of emphasize that f is the main object here, the object that the function that we want to build the next function upon, rather than the b, which is written in the syntax for iter. So we call it repeater. And with repeater, we can drop B, we can drop the main argument so that we form a relationship between the two levels of the hierarchies as function and functions. So with this, before we're going on to compute the inverse tower, let's look at how we can shorten the definition of the hyperoperation with repeater. It's a little bit shorter, and as you can see, normally you have two recursive loops for the hyperoperation. But with this, you can abstract the inner loop with the repeater and get a little bit more elegant definition. The same thing can be done for the Ackermann hierarchies. So we have a little bit more beautiful definition. So now let's try to compute the inverse tower by inverting repeater. Okay, so repeater helps us build the original tower by building the next level upon the previous level. And so we want to do the same thing for the inverse towers. We want to find a way to build the n plus 1 level with the n level. And so the key to this is to build the inverse of the repeater of a function by using its inverse. So before we go on, let's assume that a is greater than or equal to 2 every time we talk about the hyperoperation. And for the case where a is 0 or 1, those are actually trivial cases, and we handle it in our paper, but we don't need to worry about them right now. So let's formalize the upper inverse. So the thing that I've been using as inverse so far is actually the upper inverse, which is defined as a function of n. That is a minimal m for which f of m is larger than or equal to n. And if f is a strictly increasing function, you can see that the upper inverse value always exists, so it's a total function. And fortunately for us, all the functions in the two original towers are strictly increasing. And so we can talk about the inverse without any trouble. There's a more useful logical equivalence of this upper inverse relation, which is that if you have an inequality of n and m with f inverse on the left-hand side, you can transfer it to the right-hand side. It will be useful later when we try to compute the inverse of a repeater. So let's do it right now. So let us try to build the So let us try to build the inverse of the repeater from f inverse. So suppose you have this inequality of n and m. By the relation, you can transfer the repeater from the left to the right, and then you can rewrite it as repeated application by the definition of the repeater. And so you have m instances of the big F on the right-hand side. Using the relation again, you can transfer f from the right to the left when change it to the inverse. And from this, go on until we reach a point where we have m instances of the f inverse on the left-hand side and a on the right-hand side. And with this, we can infer that the value of the inverse of the repeater is actually the minimal value for which we apply f inverse to n and go below a. Okay, this is the exact way to compute what we call the countdown. So the countdown of a function is the number of times that you need to apply the function to the input in order to go below a threshold. And the threshold is a in this definition. And we have a theorem that is useful for us, which says that if f is a function that satisfies the three conditions, it's strictly increasing. The second means that it's kind of expanding on its input. And the third means that this expansion is strict whenever the input is larger than a. Then the countdown value always exceeds. It means that it's a total function. And it's also the same thing as the inverse of the repeater of f. So from this, we know that all the functions in the hyperoperation and the Ackermann hierarchies satisfy these three conditions. So we can talk about the countdown of the inverse. And we know that the next level of the inverse tower can be built with countdown from the previous level. And so, but before we compute them right away, we need to know that everything we have done so far is not meaningless. And so we want to compute countdown in Coq. the idea is simple. We just compute every repeated applications of f until we reach some point below a, the threshold. But we run into a problem because Coq doesn't believe that this computation will ever terminate. And actually, it may be right because for a general function, the countdown value may not exist. We may never go below a, so this computation may not terminate. But we can tell Coq when to stop with the worker function. Basically, we compute the repeated application. We stop when we go below a or when we run out of budget. And so this is a worker function in terms of math, and this is a Coq definition. And we proved in our paper that for our purpose of building inverse towers, a budget of n, which is also the input, is sufficient. And so we can redefine the countdown to be the value of the worker function with the input n and the budget n. So with this, we can build the inverse tower. This is the mathematical formula. This is a Coq definition. And for the hyperoperation, there are some interesting individual levels that we can build with countdown. And so if you look at the fourth level, it's the log star, which is the inverse of the titration. It's not in the Coq standard library, and the other two levels are in there, but now we can some kind of look at them. There's a connection between them using countdown, and it's kind of a nice thing to have. So if we want to build the inverse Ackermann tower in the same way as the hyperoperation, we may run into a problem. So if you look at this, the next level of the inverse Ackermann hierarchy is the countdown to ai of 1 of the next level, of the previous level. But there's a flaw, because right now the next level still depends on a, and we don't want any of a in this definition. We want them to be independent. And so we need a little bit more trick to define the inverse Ackermann tower. So this is the manipulation that we've done to redefine alpha I plus 1 of n. We start with this definition, and then you can transfer all the alpha I from the right to the left because we have the upper inverse relation. And so we can split m plus 1 to m times outside and alpha I of n inside. With this, actually, the next level is just the countdown of the previous level composed with the previous level inside. And so with this, we have built the inverse Ackermann tower independently from the Ackermann tower. So we are ready to build the inverse Ackermann function in the next step. So let's go to that. Okay. So by using the upper inverse relation, we can redefine alpha in terms of alpha k. And with this, we use the same idea of the worker function to compute it. So at each step, we compute one number in the tower with n as the argument, and we stop when we reach somewhere below, where we reach some I that satisfies that alpha I of n is less than or equal to I. This is the correct value for alpha n. Or we stop when the budget is exhausted. So because we know that by this recursive relation, the next level use the results produced by the previous step. So we don't have to compute everything from scratch. So this is a worker function. And I'll do a little bit of animation to convince you that it works. So let's say at some point the worker function is given these arguments. I write them in this form for you to compare the form of these arguments and the argument of the next recursive call. So from this, if these two conditions are met, the first one means that we haven't ran out of budget, and the second one means that we haven't reached the value for alpha n. So if these two conditions are met, it goes into the next recursive call. And using the recursive relation, we know that they're actually equal to this. And they have the same form as the previous step, but with I replaced by I plus 1. And so this is a stable way for this function to run. So if we begin with alpha 0, the next step, we get alpha 1. And in the next step, we get alpha 2. So on until we reach this point. So assuming that we have a big enough budget, we won't run out of it, so the first condition won't be violated before the second one. And the second one means once violated means that we have reached the correct value for alpha. And so at this point, we return k as the correct value for alpha. All right. So any budget that is big enough will satisfy. And so we choose n again easily, and because n is obviously larger than alpha n. And so this is the first version of our inverse Ackermann function. We fit the worker function with the alpha 0, which is by definition n minus 1. But we're not done here yet. This function doesn't run in linear time. Why? Because in the computation, we compute all the numbers in the towers, including alpha I, alpha 1 of n, which is n minus 2. But by this computation, it doesn't know that. It will try to apply countdown to it, which means that it will try to minus 1 to the input until it reaches 1. It doesn't know that it will return n minus 2 every time. So this computation will run in linear time for alpha 1, which means that it will run in n square time for alpha 2, and the whole computation will need at least n square time to finish. We don't want this. But here, because we have identified the problem, we know there's a simple improvement. You can just tell the worker that the alpha 1 level is actually n minus 2. So we fit it directly with alpha 1, which we tell it that it's actually n minus 2. And so for n below or equal to 1, we tell the worker that to return 0. This is still the correct computation of the inverse Ackermann function. So actually, by this, the previous problem has been resolved. Now alpha 2 is computed in linear time as we wanted. In fact, this improvement is enough to ensure that the whole computation runs in linear time. So actually, the recurse argument is long, so I won't tell you every details of it. But there's a sketch of the proof. So basically, in the computation, if you want to compute the next step, the total time you take is kind of like the sum of the time you take to compute all the repeated application of the previous level. And so by an inductive argument, the number of computation steps that we do during the computation is bounded above by like 4n plus a factor of log n. And in total, it's still linear. For details of this proof, you can look at our paper. And so we have defined a computation for the inverse Ackermann function that runs in linear time. This is a point of success for us. So in conclusion, there are two contributions that I have mentioned in this presentation. The first one is the inverse towers for the hyperoperation and the Ackermann function. And you have the log star and the other levels in the hyperoperation. And there are some other contributions which I didn't do here. So importantly is the binary version of the inverse Ackermann function that also runs in linear time in terms of the size of the input, which means that in terms of the value of the input, it runs in log time, which is desirable. And we also have a version of the 2-parameter inverse Ackermann function. Thank you for listening.
So I have a remark and a question. So first the remark in Coq, because you get stack overflows as soon as you write integers that are bigger than, like, say, 1,000, you should probably write it as just inverse Ackermann being 2. And the real question, it's very well known that Ackermann function is like a non-primitive recursive. It's like the archetypical example. And in your implementation, you're using high-order functions to compute the inverse Ackermann function. Do you know whether it would be possible to get a primitive recursive presentation of the inverse Ackermann function?
Oh, so you're asking me whether the inverse Ackermann function is primitive recursive?
Well, it probably should be, but is it known whether there's such an algorithm?
I'm afraid no. As per my understanding, my guessing, you can say, I don't think so, because the inverse Ackermann function is tangled with the Ackermann function. And we know that the Ackermann function is not primitive recursive. And so, although it grows extremely slowly, I don't think it's primitive recursive.
Other questions?
So it seems like the biggest difficulties you had must have been at defining the functions. Like the one slide that you showed at the beginning, that must have been the toughest part of your work, and the Coq proofs were not so hard, or were the Coq proofs also difficult?
Which slides were you referring to?
Oh, the definitions. You had this all your definitions on one slide at the beginning, and you said, oh, they all fit on one page.
Oh yeah, you mean this?
Right. So coming up with that
Yes.
seems to have been very difficult. But carrying out the Coq proofs afterward, was that
Yes.
also difficult, or was that
So
easy?
the entire Coq base, including the correctness proofs, I think it takes like 1,000 or something lines of code. These are just the Coq definition that ensure that you have a working computation of the inverse Ackermann function, which will give you the output. But in order to prove that it's the correct value of the inverse Ackermann function, yes, of course, we wrote a lot of proofs. It's in our GitHub code base, which is also in the, if you click on the preprint link on the conference, you will be directed to our GitHub page where you can see all the Coq code as well as the paper in PDF.
Okay, let's thank the speaker again.